Right. So we're finally up to Taylor polynomials, and it looks like right, we're going to be discussing Taylor polynomials and approximations. Right. So you'll sort of see how Taylor polynomials fit in with the series and all the sequences and stuff that we've been doing so far. And essentially, what Taylor polynomials are is that they're just approximations of actual functions, right? The idea being that you're trying to approximate an elementary function f of x with an infinite series, an infinite series or infinite power series, right? So some constant times x plus another constant times x squared plus another constant times x cubed and so on and so forth.
Okay, so Taylor polynomials are, so wait, there's Taylor polynomials and there's Taylor series, or is it just Taylor polynomials?
Well, the Taylor series is made of the Taylor polynomials. So
Okay.
you remember how we talked about before about partial sums, right?
Yeah.
We discussed partial sums. Essentially, what Taylor polynomials are is that they're like partial sums
Mm.
of the Taylor series, right? So just to give you an example, right? A Taylor series is when you actually take the series to infinity, right? So suppose you're trying to approximate some function f of x, right? And you figure out what its Taylor series is, right? So you have the Taylor series, a sub n times, well, I'll write it like this, c sub n, the nth coefficient, times x to the power of n, right? From when n equals 1 to n equals infinity. Right, so that's the full Taylor series expansion of the function f of x. Whereas the Taylor polynomials is just a partial sum of this series, right? So you might have something like p sub n is equal to, c1x plus c2x to the power 2 plus dot 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 up until you get to the nth term, right? So c3x, cn x to the power of n. Right, so this would be the Taylor polynomial, right, p sub n, whereas this is the full Taylor series expansion.
Okay.
Right?
So the top one is the expansion, and the bottom one is the Taylor series.
No, the bottom one is the Taylor polynomial, right, with the p,
Oh, okay.
right? Whereas the top one is the full series,
Okay.
right, from 1 to infinity. So in a sense, the Taylor polynomial is just a partial sum of the Taylor series.
All right.
Right? So this is just a partial sum. Right? And this is the full series. So the thing is, that's why I said Taylor polynomials and approximations, right? Because say, for example, your elementary function can be represented with this infinite series here, right? But obviously you can't write an infinite number of terms, right? So you write the Taylor polynomial to approximate the f of x, right? So you might approximate it to the first 4 or 5 terms. So you just sum until you get to term number 5, term number 4, whatever your approximation is. Right, but we're gonna get more into that. But the idea is we're gonna focus first on Taylor polynomials. Okay. Okay, so Taylor polynomials and approximations. Right, so Taylor polynomials and approximations. And right now, we're going to look at approximations of elementary functions. polynomial approximations of elementary functions. Okay, so the whole idea is to show how polynomial functions can be used as approximations for other elementary functions, right? So the thing is that to find a polynomial function that approximates another function f, you want to start by choosing a value c that's in the domain of f, right? Where the polynomial and f have the same value, right? So for let's say to find a polynomial p that approximates another function f, so another function f of x, we start by choosing a number c in the domain of f, at which f and p have the same value. So essentially f is equal to p, right? So in other words, we want a value c so that p of c is equal to f of c. Okay, so what this essentially means is that your graph of f and p pass through the same point, right? So we're going to say graph of f and p pass through the point c comma f of c. Okay, so that's the first requirement, right? You want your polynomial and your function to be equal at that point c. Okay, so when we make this kind of choice, essentially what we're saying is that we're approximating the polynomial, or we're saying we're approximating our function f with the polynomial p, and the polynomial p is said to be expanded about c, right? So c is acting like the center about which we're expanding this polynomial. So we're saying that p of x is centered at c. So that's the first thing we want, right? So we want p and f to be equal at c. But the thing is, that's not enough, because if you want your polynomial p of x to properly approximate f of x, right? You also want your p of x to have the same tangent or the same derivative value when x is equal to c, right? So in other words, the two functions must be sloping the same way. Right, so we're going to say we also want the two functions to have the same slope. Right, meaning that we want P prime at C to be equal to F prime at C, right? So we're going to say we want P prime of C equals F prime of C. Right? So far we've put two requirements on this polynomial, right? Now, with these two requirements, what you can create is called a linear approximation. In other words, you're just creating a straight line that passes through C comma f of C with the same slope as f of x when x is equal to c, right? Okay. So, right, I was going to show you sort of an image of what this looks like. Okay. Right, so the dark line is the f of x, right? The actual function here.
Mm.
And you see that by making these two requirements, right, that our polynomial has to equal f when x is c, and also its first derivative must be equal to the first derivative of f when x is c. What that means is that the only polynomial that satisfies just these two requirements is just a straight line. So essentially we created a tangent line here to our graph of f, right? So we're going to say that the two requirements that we just listed create a tangent line approximation. Okay, so let's say our two conditions. So our two conditions, P of C equals F of C, and P prime of C equals F prime of C, creates a tangent line approximation. Okay. So this is the fundamental thing, right? The fundamental thing to understand here is that we're creating, first of all, we're requiring the polynomial to be equal. Its derivative has to be equal. So what happens when we require that the second derivative also has to be equal and the third derivative also has to be equal, right? Essentially, the idea is the more derivatives that you put the requirement on that it must equal that same derivative for f, the more the resulting function or the more the resulting polynomial looks like f, right? So our Taylor approximation essentially just ends up being a series of terms that add up together, right? But ultimately approximate the value of f of x near c. Okay, so let me show you an example of what a first degree polynomial approximation looks like. So in this example, it says for the function f of x equals e to the power of x, find a first degree polynomial function, right? First degree polynomial function. P1 of x equals a naught plus a1x, whose value and slope agree with the value and slope of f at x is equal to 0, right? So in this example, our f of x happens to be the exponential function, right? E to the power of x. So we're going to say, first off, our f of x is e to the power of x. And since we're using a first degree polynomial approximation, right, that means that our p of x will be written as p1 of x, right? The index at the bottom represents the degree of the polynomial. And for first degree polynomial, well, it's just equal to the intercept a0 plus the slope a1 times x. Okay, so our first condition is that our polynomial must be equal to the function when x is equal to c, right? So we're gonna say we require, and also keep in mind that our c value is 0, right? So we're gonna say our c is equal to 0. So we require p of 0 must be equal to f of 0, right? So let's calculate f of 0. Well, f of 0 is just e to the power of 0, so that gives us 1. Which means that p of 0, right, our p of 0, if we substitute 0 in here, we get a0. Right, so therefore, a0 must be equal to 1. So that's the first thing. A0 equals 1. Right, our next condition is that the first derivative of p must be equal to the first derivative of f, right? When x is equal to 0. So I'll say we also require p prime of 0 equals f prime of 0. Now, p prime is just the slope of this linear function. It's just a1, right? So we're going to write a1 must be equal to f prime at 0. Now, what's the derivative of e to the power of x?
E to the power of x.
Right? E to the power of x, right? So we evaluate e to the power of x at x equals 0. We get 1. Therefore, a1 must be equal to e to the power of 0, which is just 1. So we have a1 equals, write it like this, a1 equals 1. Right? So we figured out what the constants in our polynomial happen to be, right? We got a0 equals 1, a1 equals 1. So our polynomial will be p1 of x is equal to 1 plus x. All right, this is our first degree approximation. So this is our first degree polynomial approximation. Okay?
Yeah.
All right, so let's just sort of recap on what we just did, right? So we defined two conditions that provide us with a first degree polynomial approximation, right? And those two conditions are that the value of your
P of c equals f of c, and
Right.
p prime of c equals f prime of c. So
right.
the two conditions have to like be equal to each other.
Well, yeah, exactly, right? In the two conditions, the polynomial and the function must equal each other, right?
Yeah.
right? So as long as you meet those two conditions, you can create a first degree polynomial approximation, right? This is also called a linear approximation. And that's what we used to create this polynomial. And that's the same polynomial over here, right? So you see that the polynomial happens to be a straight line. It passes through c f of c. It's just that for us, our c happens to be 0, right? Over here, they just put a general c value. So it passes through that point, and same idea with the f of x. It also passes. And they share the same property, that they have the same slope, the same derivative value at that point. Okay, so let's move on to the next thing, because we're going to see that we can extend this to higher derivatives. Right? We're simply requiring that the second derivatives are equal, third derivatives are equal, so on and so forth.
Okay.
Okay. So now we'll take a look at what a second degree approximation looks like. Okay. So from the first approximation that we did, right, although we got a nice tangent line, that tangent line is going to approximate your f of x when x is reasonably close to the c value we use, right? So our c value was 0. So as long as our polynomial, our x values are reasonably close to 0, then the approximation is good. Okay, so let's see what happens when we create a second degree approximation. Okay, so we'll say that for a second degree approximation, and we're still using the same example in the last on the last board, but for a second degree approximation, right, we require that p double prime at c equals f double prime at c. Okay. So we can apply that to the same example we just did. All we have to do is take the second derivative of f of x, and we also have to generate a second degree polynomial, right? And just set its second derivative equal to the function's second derivative. All right, so we can say we require that p second prime of c equals f second prime of c. So we'll say let p2 of x equal a naught plus a1x plus a2 x squared, right? So this is a second degree polynomial. Right, and remember that we've already found that a naught and a1 are both equal to 1, right? A naught equals a1 equals 1. So let's take the second derivative of p2, right? So we'll say p2 double prime of x. So p2 double prime of x happens to be 2 times a2. Okay. And we'll say if c equals 0, then p2 double prime of 0 is just equal to 2 times a2. And we want that to be equal to f double prime of 0, right?
Yeah.
Right, and we're still using the same f of x. Right, so in fact, let me just write that here, right? So I'll say, suppose f of x is equal to e to the power of x, and p2 of x equals a naught plus a1 plus a1 times x plus a2 times x squared. Right, so this is our f. That's our second degree polynomial, and we're doing a second degree approximation. Okay, so now we know that 2 times a2 must be equal to 1. Right, so we have 2 times a2 is equal to 1, which means that a2 must be equal to 1/2. Okay, so that means that, say, therefore p2 of x is equal to 1 plus x plus 1 over 2 times x squared. Right, so this is our second degree polynomial approximation. Okay, so this pattern continues to whatever number of terms you want, whatever number degree of your polynomial that you want. All right, so we can make a general statement here. We can say, in general, the nth degree polynomial approximation of f of x equals e to the power of x will be p sub n of x is equal to 1 plus x plus 1/2 x squared plus 1 over 3 factorial x cubed, all the way until you get to n. So it'll turn out to be all of this summed up to 1 over n factorial times x to the power of n. All right, so we're going to say this is approximately equal to e to the power of x. Okay, so let's do an example here where we try to find the fourth degree Taylor polynomial, or we could say the fourth degree polynomial approximation for e to the power of x, right? So say determine the fourth degree polynomial approximation of e to the power of x. Okay. So according to our result over here, right? The nth degree polynomial approximation for e to the x is just the sum of these terms up to the nth term, right? So this is our first term. Well, yeah, this is our first term, but this is the 0th degree approximation. This is the first degree approximation. This is the second degree approximation, and so on and so forth, right? So the degree is what's represented by n, right? Not the term. So if I say 0th degree approximation, well, then it's the first term. But if I say first degree approximation, it's up to the second term.
Okay. So unlike with sequences and series, it's not like when it says 0th, like we're starting from like the first term, or like,
Yeah.
you know what I mean? Like,
no, yeah, I see what you mean, because some of the sums start from n equals 1, right?
yeah.
But this one actually starts from n equals 0, and then n equals 1 and so forth. So just keep in mind, right, when we say the nth degree polynomial approximation, we're talking about building the polynomial up until the nth degree, right? So first degree polynomial approximation means these two terms, because this is linear to first degree polynomial, right?
Okay.
Right, so in this case, we want the fourth degree, okay? So that means we want p sub 4, right? So we're going to say p sub 4 of x, according to this formula, is you build it up until you reach n factorial, so 4 factorial. So we're going to have 1 plus x plus 1 over 2 factorial times x squared plus 1 over 3 factorial times x cubed plus 1 over 4 factorial times x to the power of 4. Right? And this is approximately equal to e to the power of x. Okay, so just want to show you a quick example here. Right, and
Oh, can you scroll up a little bit for a second?
oh, all right.
Okay.
Cool. So with this example, we're not going to work it out, but I just want to show you the result and how good these approximations can be. Right. So for the example, it says to construct a table comparing the values of the polynomial P3. So this is a third degree polynomial, right? And we're comparing its values with f of x equals e to the power of x for several values of x near 0. So our C, our center, is 0.
So we're doing limit, I think this is like numerical limits.
Not numerical. Well, yeah, it's a numerical approximation, I guess. I guess you
Yeah.
can say, right? But the idea here is that we're trying to show how good the approximations are, and we're comparing the polynomial values to the exponential values, right?
Mm.
So our approximation is 1 plus x plus half x squared plus 1 over 3 factorial x cubed, right? So this is the P3 values. So obviously when you're at 0, the center, the polynomial equals the exponential value, right? They're the same, right? But say, for example, you move, 0.1 units away from 0 in either direction, whether it's in a positive or negative direction. This is the polynomial's value. If you plug in x equals 0.1, you get 1.105167. If you plug in x equals 0.1 for e to the power of x, you get 1.105171. So you see, the approximation is good up until the 4th decimal place. Right, so it's good up until the 4th decimal place. If you go to 0.2 units away, right, it's good up until the 3rd decimal place, and if you go 1 unit away, it's only good, I guess, up until the 1st decimal place, and even that, it's a little bit off, right? So it's really good when you're very close to the center, but the further away you go, the worse the values. But keep in mind, this is only a 3rd degree polynomial. Higher degree polynomials would give you a better value the further away you go, right? Give you better approximations even when you go further out.
Mm.
Okay, so let's move on to the next thing. Okay, so let's get into Taylor and Maclaurin polynomials. All right, so Taylor and Maclaurin polynomials. So with the example that we just did, right, we allowed our center C to be 0, right? C was equal to 0. Right. Now, suppose that we wanted to expand our polynomial about any arbitrary value C, right? So it's convenient to write the polynomial in the following form. So for an expansion about an arbitrary value C, it is convenient to write our polynomial in the form P sub n of x is equal to a sub naught plus a sub 1 times x minus c plus a2 times x minus c squared, right, and so on until a sub n times x minus c to the power of n. Okay. Now, the goal here is to identify what the coefficients are, right? So we are interested in determining the coefficients. Right, so our coefficients are a naught, a1, dot, 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 to an of the polynomial. Okay, because if we have the right coefficients, then the approximation, the approximation is better, right?
Mm.
So it turns out that our coefficients are the following. Right, so our coefficients turn out to be a naught equals f of c, a1 equals f prime of c, a2 equals f double prime of c divided by 2 factorial. Right, and for the nth degree, we have the nth derivative at c divided by n factorial. Right, so this would be an. Okay, so your first coefficient, the a naught, is f of c, a1 is f prime, a2 is f double prime, divided by 2 factorial, and so on and so forth until you reach a sub n, right? F, the nth prime of f at c. Okay, so this is the difference between the Taylor polynomials and the Maclaurin polynomials. The Taylor polynomials are polynomials centered at any arbitrary value c, right? But the Maclaurin polynomial is a special case of the Taylor polynomial when c happens to be 0, right? So you're centering it at 0. So you see here, all of your coefficients are evaluated when c is equal to 0 for the Maclaurin polynomial. Whereas for the Taylor polynomial, your coefficients are evaluated at with whatever c value you're centering the expansion about. Right? So if f has n derivatives at c, then the polynomial p sub n is equal to f of c, f prime of c times x minus c, and so on. Right, so this is the nth Taylor polynomial. Right, and then for the Maclaurin, you're centering it at c is equal to 0. So this is the nth Maclaurin polynomial. Okay, so really the example that we did in the previous board was an example of the nth Maclaurin polynomial, right? When we did the 4th degree of e to the power of x centered at x equals 0. Well, actually, that one we didn't. No, yeah, we did. We centered it at x equal to 0. right? So that one was the was an example of the Maclaurin polynomial.
Okay. So so there's Taylor polynomials and Maclaurin polynomials.
Right.
And the difference between them is, at least with the Taylor polynomial, what I've gotten is that like in order to get like, I think it was the first no, it wasn't like it was like the first, what was it called? Let me find it. First degree, or no. There's something else. There's like two conditions, and then they allowed you to get your first linear approximation. No, you were able to get a linear approximation if you were able to fill like the two conditions, which were P of C equaling F of C and P prime of C equaling F prime of C.
Right. 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 So that was to
And
get a first degree polynomial approximation.
yeah.
Right. Which is also called a linear approximation.
Yeah.
Right. Right. And then we moved on from there to do an example where we wanted the second degree approximation. Right. So for that, we had to write a second degree polynomial, right? So that's why we wrote a naught plus a1x plus a2x squared. That was our second degree polynomial. And then we applied the conditions again, right? So p of c must be equal to the function at c. P prime must be equal to the function f, the function's derivative at c. But since we were doing a second degree polynomial approximation, that means the second derivatives also must equal each other, right? So we had to take the second derivative of f and of p, evaluate them at 0, and set them equal to each other, which we did. Now, now we're talking about an nth degree polynomial expansion, right? So for any degree you want, any nth degree that you'd like. So in order to make this expansion work and approximate properly, we ended up having to take derivatives, right? Because remember, the conditions is that not only must the function value and the polynomial value be equal, but the derivatives also must be equal, right? And in that process of requiring the derivatives to be equal, we were able to obtain the coefficients. So the coefficients are a naught is f of c, a1 is f prime of c, a2 is f double prime of c over 2 factorial, and so on and so forth. Now, I didn't show the whole process from going from this step to this step here because it's a bunch of derivations. It's going to take a lot of time. But what's important is the conclusion here, right? And the conclusion is that the coefficients are just derivatives of the function at that point divided by factorials, right? So from there, our conclusion is that P sub n centered at any value c, it could be 0, 1, 2, negative 4, whatever, right? Centered at any value c can be written as this expansion here, right? And that's called the Taylor polynomial. The Taylor polynomial, you can center it wherever you like. The Maclaurin polynomial is just the case of the Taylor polynomial when you center at 0. So you set c to be equal to 0. And that gives you your Maclaurin polynomial. Okay, so Maclaurin polynomial is a special case. We'll write it here. We'll say special case of Taylor for when c equals 0. Okay, I think this is the best one I can find. But let me show you this. All right, so take a look at this this animation here.
Okay.
Right, so the function is e to the negative x times sine of x. Right, so that's the function there. So it's the blue curve here, right? The green curve is the Taylor series approximation for the blue curve, right? So you see that we're using a center of 0, right? Which means that the green curve is going to pass through the same point that the blue curve passes through when x is 0, right? So right here. But as you increase the number of terms of that polynomial, it starts to like wrap around the blue curve, right? So the higher the degree polynomial you use, the better the approximation. Right, so this is like an order of, right, 11th order polynomial, and it makes its way all the way up until like 3, I think, right? So for the case where you have an infinite number of polynomials, then it perfectly represents the function at all points. Okay, so let's move on to the next thing here. We can actually do a quick example. Okay, so in this example it says to find the Taylor polynomial P0, P1, P2, P3, and P4 for when f of x is equal to natural log of x, centered at c is equal to 1, right? Okay, so let's start with P0, right? Very simple. We don't even have to take any derivatives. But when you're doing these kinds of problems, right? It's best to first list out all of the values, all the derivatives and the derivative values, right? Once you've listed them out, then you start writing out the polynomial expansions, right? So since we're going up until P4, right, we need the first 4 derivatives, right? So we'll start at f of x, right? So f of x is just natural log of x. And since we're centering at c is equal to 1, that means we also need f of 1. Right? And remember, natural log of 1 is just equal to 0. Okay, so now we need the first derivative. Right? So natural log of x, its first derivative is just 1 over x, right? Now we can write f prime at 1, which is just 1 over 1, which is equal to 1. Now we need the second derivative, f double prime at x of x, which is just the derivative of this. That gives us negative 1 over x squared. And we need f double prime at 1. So this gives us negative 1 over 1, which is equal to negative 1. Okay, so our third derivative, right, we can get that by writing this as negative x to the negative 2, right? So we just have to take the derivative of negative x to the power of negative 2. Well, that just gives us 2 factorial. say f double prime of x, or f triple prime of x. This gives us 2 factorial over x cubed. So this is f triple prime at 1. That gives us just 2 factorial. Right, and then we can take the 4th derivative here. Alright, so this here is 2 factorial times x to the negative 3. Right? If we take the derivative, that gives us negative 3 factorial over x to the power of 4. Right? Because we're multiplying the negative 3 by the 2 factorial. So that turns out to be just 1 times 2 times 3, 3 factorial. Negative sign makes the whole thing negative. So now we can do 4th derivative of f at x equals 1. This gives us negative 3 factorial. Right, so negative 3 factorial is just negative 3 times 2 times 1. That's just negative 6. Okay, so now that we have all the derivatives that we need, we just need to write the polynomials, right? So our P naught so our P naught of x, according to our Taylor polynomial formula, P naught of x is just f of c, right? So it's just going to be f of 1, which is 0. So our P1 of x, according to the formula, is going to be f of c plus f prime of c times x minus c. So this is going to be f of 1 plus f prime of 1 times x minus 1. Right? And if we substitute what our values are, it's just 1 minus x minus 1. Or actually, sorry, the minus is for f double prime. This should be positive. So it's going to be 1 plus x minus 1. Okay, so now we can do P2 of x. This is f of 1 plus f prime at 1 times x minus 1 plus f double prime at 1 times, well, over 2 factorial times x minus 1 squared. Right, so let's write out what this comes out to be. It's just going to be 1 plus x minus 1. And f double prime is just negative 1, so this would be minus 1 over 2 factorial times x minus 1 squared. Right, so it's just the same pattern. So I'm just going to write out the formula now for P3. All right, so P3 turns out to be hold on, I think I made a mistake. Let's go back to P1. P1, I accidentally put f of 1 as 1. It should be 0, right? F of 1 is 0. So this is 0 here. And I made the same mistake here as well, so it should be 0.
Oh, right, for so f prime up there? Okay.
Yeah, for the f of 1?
Yeah.
I accidentally put 1. Alright, so it's 0 plus this and 0 plus this. Alright, so I'll just skip past the 0 this time, but for P3, you're going to get x minus 1 minus 1/2 of x squared, x minus 1 squared, and plus 1/3 of x minus 1 cubed, right? So that's just if you follow the formula written here using the values written here. Okay, and then we can write P4. So P4 is going to be x minus 1 minus 1 over 2 x minus 1 squared plus 1/3 x minus 1 cubed. And we might have another minus sign here. So this is minus 1 over 4 x minus 1 to the power of 4. Right, so it's pretty tedious if you're writing an nth degree polynomial where the n value is large. Right, you just have to be really careful when you're defining your derivatives and their values before you place them inside the formula.
Yeah. Okay, so it was basically just like listing out all the values from f of basically 0 to f of 4. Well, I don't know how to describe it, but like I just know that it was like basically p0, p sub 0 to p sub 4.
Yep.
Like having those laid out and having the primes of those laid out too, I believe.
Yeah.
Because on one side it had natural log of x, and on the other side it was 0.
Yeah.
And yeah, it was just, let's see.
Right, so you want to first write out all the derivatives you need for your f of x, right? Then you want to evaluate them at whatever center you have, right? So in this case, we were centered at c equals 1.
Yeah.
So you need to evaluate all your derivatives when c is equal to 1. Once you have that, it's just a matter of plugging it into the formula, and that's it. Right? So for P4, right, we did the 4th degree polynomial, and we summed all the terms until we reached a power of 4.
Okay.
Right, so this section is pretty it's kind of longer than the other ones because we still need to cover the remainder theorem for Taylor polynomials and Taylor approximations. Right, we need to cover the remainder theorem and also determining the accuracy of a Taylor polynomial. Right, so for now, let's take a look at this was a Taylor, well, this is a Taylor series, a Taylor polynomial example, right? But suppose I said, okay, let's try to find the Maclaurin polynomial approximation for this, right? So remember, Maclaurin is just the special case of Taylor for which c is equal to 0. So it'll be the exact same result except our c is equal to 0. So you're going to have to change all these derivatives, evaluate them when they're at 0, right? And then plug them in here. Right? And everywhere you have your x minus 1, you would write x minus 0. Or you can just ignore the 0 altogether and just write x, right? All right, let's do an example with Maclaurin. Okay, so in this example, we want to find the Maclaurin polynomials P0, P2, P4, and P6 for f of x equals cosine of x. And then what we're gonna do is we're gonna use P6 to approximate the value of cosine of 0.1. Okay, so remember the steps. First, we need to calculate all of our derivatives that we're gonna need. And then we're gonna have to evaluate them. So the good thing is we're not gonna need to calculate up until the 6 derivatives, because when it comes to sine and cosine, there's sort of a pattern that you get when you start evaluating the derivatives at x equals 0. Right, so we're gonna say first, determine the necessary derivatives. Right, so let's start with f of x. Right, so f of x is equal to cosine of x, which means that f of 0 is just equal to 1. Okay, so if we do f prime of x, we're going to get negative sine of x. So now if we do f prime of 0, this is just going to be negative sine of 0, which gives us 0. If we take our second derivative, we're going to get negative cosine of x. Evaluated at 0, we get negative 1. Right, so third derivative. This is going to give us positive sine of x. Right, so evaluate that at 0. We're just going to get 0. Okay, so at this point you can sort of see a pattern here, because if we take the fourth derivative, we're just going to go back to cosine, right? Which means that we'll be starting the pattern all over again. Negative sine, then negative cosine, then positive sine. So we don't have to keep taking the derivatives up until the sixth derivative in this case, right? We know that we can use this value. Well, we can use this value here as the first value, or as the first coefficient. This one, then this one, then this one, and then repeat the cycle. Right, but since you see that every second coefficient is actually equal to 0, right, then that means that all the odd terms are going to vanish. Right, so remember, this one corresponds to your 0th power, or sorry, your 0th derivative, whereas this one corresponds to your first derivative, right, f prime. So the Maclaurin polynomial, like the term in the Maclaurin polynomial corresponding to f prime, that part is going to vanish, right? But this part is going to stay, right? The second derivative part is going to stay, and then the third derivative part is going to vanish, right? So this is what it's going to look like. Right, if we write out P6, right, so P6 of x, right, so according to our formula, right, it's going to be f of 0, which is 1, plus 0 multiplied by x minus 0, right? But, you know, we don't have to write the minus 0 part. We'll just put x. And then minus this one here, right? 1 over 2 factorial times x. This would be x squared. And then, let's see. Then this would be a plus 0 times x cubed. We did this one, 0, right? So we have 1, 2, 3, 4 terms already, which means we got to start back up over here. So this would be plus 1 over 4 factorial times x to the power of 4. Then again, we get to a 0 coefficient here. So 0 times x power 5. And then here we have a minus 1. So minus 1 over 6 factorial times x to the power of 6. So this is our P6, right? Our degree 6 polynomial. So all of these cancel, right? These are just zeros. All right, so that means our P6 of x can just be written as 1 minus 1 over 2 factorial x squared plus 1 over 4 factorial x to the power of 4 minus 1 over 6 factorial x to the power of 6. Okay, so the next part is to evaluate P6 at 0.1, right? So this is approximately what cosine equals to when you're really close to 0. So we're going to evaluate our P6 at 0.1, and then we're going to compare it to the actual cosine of 0.1. Alright, so if we substitute x for 0.1, we end up getting approximately 0.995 004165. Okay, so cosine of 0.1 is the same value as P6 of 0.1 up to, I believe, 9 decimal places. All right, so this is a very good approximation. Okay, so just as a quick recap, right? Our example wanted us to find the Maclaurin polynomials, P0, P2, P4, and P6, right? So we kind of skipped the P0, P2, P4 part, but from our results here, you can see clearly what the P0, P2, and P4 would be, right? Your P0 would just be this part. Your P2 would be this part. Well, your P2 would be this part. Your P4 would be all of this. And then, of course, your P6 would be the entire thing up until 6th degree. Right? And it wanted us to use P6 to evaluate cosine or to approximate cosine of 0.1, right? So we simply substitute 0.1 in there and see what we get. And it turns out that our approximation is accurate up until 9 decimal places. Right, so it's a very good approximation. And yeah, do you have any questions about this example?
Not really. Like, yeah, like it pretty much is like everything we've been doing this entire this session. Like, I get it. It's about like using I believe this one was a Maclaurin polynomial to get an approximation, and also to see how good that approximation was, because like,
Right.
but I'm pretty sure like the Taylor and Lauren polynomials are just techniques using to like find approximations of like numbers, so you can see, I guess, like
Approximation of functions, right?
Oh yeah. Like, so you can see how close like I'm trying to think of a scenario you would probably like use this in. So I guess like maybe experiments, because in experiments you want to find something that's the closest to your value, or like the value you're targeting.
Yeah, because sometimes, for certain functions, it's easier to just use an approximate value than to try to get the actual value, right? So there are certain cases where it's better to use an approximation. And also, in terms of like some really important results in engineering, right? Some of the derivations are done using Taylor approximations. Because I've tutored in mechanics of materials, and some of the stress formulas that you arrive at come from using these kind of Taylor approximations. And they typically use like a first or second degree approximation, and then from there they're able to obtain a formula. So, they all have their applications in different fields, right? So remember, the math is just showing you the general rule, right? And then these rules and these formulas are then applied to like physics and engineering problems.
All right. Cool.
All right, man. So good work today. I'm gonna post these up, and I've also uploaded one of our older sessions onto the playlist. And next week we'll definitely be finished with Taylor polynomials, and the next thing after that is power series.
Cool.
Right. All right, so I'll see you then.
All right. Merry Christmas.
All right, you too. New Year's.
Oh yeah, same.
Yeah.
All right. Bye.
Bye.